All right, here's a practice problem with a long straight wire that carries some current. So let's figure this stuff out. Let's see, we've got a wire here. Let's say it's carrying the current upwards, 5 amps. Okay. Now, as we've said, the wire itself generates a magnetic field. If you take your right hand and you put your thumb towards the top of the page and you wrap your fingers in a certain way, that's going to create a magnetic field. Your fingers on this side of the wire should be pointing into the screen. Into the screen, we use X's. So there'll be a magnetic field into the page or into the screen this way, and your fingers will be curling out of the page over here, out of the screen. Okay, that's your right hand rule number 1. Thumb in the direction of the current, right? Hitchhiking, your thumb goes in the direction of the velocity, and your fingers curl the way the B field goes. That's right hand rule number 1. So here we've got that. So as this is going to create into the page that way, out of the page that way, it's going to create a magnetic field swirling around like so. Now, near this wire, pretty close to this wire, they put 4 millimeters away from it, they put a proton, positive thing, over there, 4 millimeters away from the wire in the same direction. At one instant, the proton 4 mile travels. Okay. And it's traveling parallel to the wire in the same direction as the current. So this thing's got a velocity that way. That's supposed to be parallel. Well, imagine those two lines are parallel, but you're okay. All right, so the proton is moving that way at 1,500 meters per second. Holy cow, we got 5 amps of current, some proton moving that way just at an instant. Now, you could work all this out and you'd get the same results if you put it on the other side of the wire in a second. You know, if you put the proton on the other side, you'd still end up with the same results. But here we go. If that were the case, yeah, you're still going to end up with the same answers. Okay. 4 mils away. What do we need to do? Find the magnitude and direction of the magnetic force on the proton. So the proton is in this magnetic field. We have to figure out the magnitude of the magnetic field created by the 5 amp current. So the magnetic field, Ampere's law, mu naught times the current over 2 pi r. Mu naught is 4 pi times 10 to the minus 7th. The current is 5 amps. 2 pi is 2 pi. And R is 4 millimeters or millimeters. 4 times 10 to the minus 3 meters. I should include my units for mu naught, Tesla meter per amp, right? Tesla meter per amp. Okay. Our meters will end up canceling out. We're going to end up, our amps will cancel out, our meters cancel out, we're going to end up with Teslas. So let's do this math. 4 pi Turn on the calculator. Here we go. 4 times pi equals that. 1.26 times 10 to the minus 7th, or 12.6 times 10 to the minus 6, or 1.26 times 10 to the minus 7th. So 4 pi times 10 to the minus 7th, might as well write 1.26 times 10 to the minus 6 times 5 divided by 2 pi is 6.28 times 4 times 10 to the minus 3. Let's do all this arithmetic. 1.26 second e negative 6 times 5 gives you that, divided by 6.28 divided by 0.004. And we get, let's go 2.51. 2.51 times 10 to the minus 4 Teslas. That's the B field. They want to know the magnetic force. The magnetic force, recall, magnetic force is QVB. QV sine theta B. But here, since the V is that way and the B is into the page, they are at right angles. Sine theta, since they're perpendicular, sine 90 degrees is 1. So we just get that. It's a proton. Remember the charge of a proton? 1.6 times 10 to the minus 19th coulombs. The velocity, you were told, was 1,500 meters per second. And the B field, we just calculated to be 2.51 times 10 to the minus 4 Teslas. So what is the magnetic force? 1.6 second E, whoops, wrong button, second E negative 19 times 1,500 times 2.51 second E negative 4. All of that equals basically 6 times 10 to the minus 20. 6 times 10 to the minus 20 newtons. Yeah, that's not very nice. Let's redraw that. Magnetic force is that. The direction of the magnetic force, using the right-hand rule, is going to be into the wire. If I put the proton here, the magnetic force using our right-hand rules will be this way, towards the wire. If we had put the proton over here, oh, we used the wrong blue. If we put the proton over here and had it moving up this way, again, using your right-hand rule, fingers pointing towards you, thumb going up the straight edge, the magnetic force would be into the wire once again. The magnetic force would be this way, into the wire. So depending on wherever you put the proton, it really doesn't matter. The force it's going to feel is going to be moving into the wire. On this side, the force is, let's say, to the left, which is towards the wire. On the other side, when the proton, if the proton were on the other side of the wire, the force would be directed to the right, but it still would be toward the wire, toward the current carrying wire. All right.